Okay, so we are going to go ahead and start where we left off yesterday, which was on example problem number 31. So we talked about yesterday, let me go ahead and present this. We talked about yesterday that you have to find and solve for both of these forces to find the net force on this, force net. We want to know what is that. So once we find these two values, we can use Pythagorean theorem to solve for what that resultant net force is. Sorry, that doesn't look like net at all, but you get the idea. But in order to find those two values, we need a couple things that are not here, unfortunately. So first thing is when you're solving for these, and my suggestion to you is to pause the video, see if you solve for things. I'll give you the answers to them. We were having a lot of trouble in period 3 yesterday, trying to figure out what these values were and actually getting the correct answer for them. So don't just assume you're going to be able to type everything in and everything's going to come out perfectly right. Because when you do the book work, you'll end up with wrong answers, and the test, obviously, the same thing. So remember, force of gravity is G m1 m2 all over r squared. What we're missing here from this problem is the r values. So the r value, the radius or the distance from the moon to the sun, which you don't have that given in here, is 1.5 times 10 to the 11th meters. And the radius of the moon to the earth, we're going to struggle here. Oh my goodness. Forget that. Radius of the moon to the earth is 3.84 times 10 to the 8th meters. 3.84 times 10 to the 8th meters. So with those two values, see if you can solve for the force of gravity, the gravitational force between the moon and the earth, and the gravitational force between the moon and the sun. And then again, once you have those two values, remember this force of the moon between the moon and the sun, that actually can be written out here as this vector, and then you can obviously treat that as a right triangle and just use a squared plus b squared is c squared. So go ahead and solve these as two separate problems. You're going to solve force of gravity equals big G times, if I were specifically solving this for, say this was the force, gravitational force between the moon and the sun. I'm struggling here with this. Sorry, everybody. Then I would have the mass of the moon and the mass of the sun. And then, of course, the radius between the moon and the sun squared on the bottom. And then I do the same thing with the force of gravity between the moon and the earth. I just replace the same values. So go ahead and solve for those. Pause the video, solve for them, see if you can get them. And even if you want, use Pythagorean theorem to solve for the net force. What you should get for these is the force between the moon and this isn't the final answer. This is just the steps in between. Actually, let me give you the final answer. That way you know what you're shooting for. 4.77 times 10 to the 20th newtons is the net force, that resultant force that the moon feels being between the sun and the earth. And if you did not get that, let's check to see if you got both of these. Remember I said yesterday, going back and checking all of your mathematics, making sure you typed things in right, making sure everything was converted into meters, kilograms, and seconds is important. So the force between the moon and the earth is 1.99 times 10 to the 20th newtons. And the force between the moon and the sun, 4.34 times 10 to the 20th newtons. And then obviously using these two values, squaring them and taking the square root, you should end up getting this. Okay, moving on. This is one of those problems I was talking about yesterday when we said the gravitational acceleration or the gravitational field strength on different places on the Earth changes. It's not always exactly 9.8 meters per second squared. It can be a little bit above or below. So if we're below sea level, closer to the center of the Earth, gravitational acceleration or gravitational field strength is going to be a value that's larger than 9.8. And then if you're up on the top of a mountain farther away from the center of the earth, that gravitational field strength is going to be less than 9.8. So we're up on Mount Everest here. You want to make sure that you understand that the gravitational field strength, because we're up on a mountain, is going to be less than 9.8, but it should be somewhere around 9.8. You're not going to get something ridiculous like 5.6 meters per second squared. You're not going to get anything drastically different than 9.8. It's just going to be a slight variation. So I do want to do a quick derivation of the equation in this before we solve for it. So first of all, let me draw a picture. If we're up on a mountain, we not only have to measure our R value from the center of the earth, so we have to measure the radius of the earth as well as the height of the mountain. And those two things together are going to be the radius that we use in the equation. So this question is asking us, what's the acceleration due to gravity? So it's asking for little g. It wants to know little g when you're standing up on Mount Everest. In order to figure out this value, this is going to seem silly that I'm going to write this equation, but it helps us to understand. So force of gravity is equal to force of gravity. Now, we used to know force of gravity is just mass times gravity, but think for a second, because we know in our equation for force of gravity that's up on the board, big G m1, m2, all over r squared, because that's basically what we're going to set it equal to. We have two masses, m1 and m2. When I'm dealing with this side of the equation, and I have the force of gravity on an object that's accelerating down toward the earth, what mass am I speaking of? Well, in this particular problem, we have gravity on an object. We have some object up here, a person, whatever, a ball, doesn't matter what the object is. So I'm going to call it a person just for the sake of. So we have the mass of the person times the acceleration due to gravity is equal to what we just learned as force due to gravity equation. So big G times the mass of the person times the mass of, and what's our other object here? Well, it's the earth. That's the other object that's being, the forces are existing between. And then we have the radius between the person and the earth. So the reason why I'm showing you this is so that you can see the mass of the person on both sides of this equation cancels out. And we're left with the gravitational field strength is equal to big G, mass of the earth, all divided by the radius between the person and the earth. So I just substitute in what I know. Big G, 6.67 times 10 to the negative 11th. Remember, that's a constant value. It doesn't change. Mass of the earth. Remember, I told you to, I don't know if I told you this yesterday or not, but that's a value that's really important to keep. You're going to use it a lot. Times 10 to the 24th kilograms. And the radius. So now we need to figure out what the radius is. I'm going to put that in. 5.98 times 10 to the 24th. And then all divided by the radius. Now, this is not the radius of the Earth. This is not the elevation that Mount Everest is. This is the entire thing together. So another number I told you to remember was the radius of the Earth, 6,380 kilometers. And obviously we need to change it to meters. So 6,380, add 3 zeros, and square it. Sorry, I didn't put that over here. The squared value. If you were thinking I need to square that, you were right. Okay, so go ahead and do the mathematics for that. Pause the video, do some calculations. Know and understand that if you don't get the right answer in the end, go back and check. And also knowing that acceleration due to gravity or the gravitational field strength on the Earth is supposed to be around 9.8 meters per second squared. So hopefully you get a number that is around 9.8, but slightly less because we're up on the top of a mountain. And you should get 9.77 times 10 to, not times 10 to the anything, meters per second squared, which is what we expect, slightly less than 9.8. All right, so this problem, it's the last one I'm going to do with you, but this is kind of a big problem. So first thing that we need to know and understand is what a geosynchronous satellite is. Do you know what a geosynchronous satellite is? Geosynchronous satellites are ones that stay above the same point. So if there's a geosynchronous satellite above Ohio, that means it always stays above Ohio. So sometimes problems in the AP physics world expect you to know some common knowledge. They don't necessarily expect you to know, I guess maybe they are expecting you to know what geosynchronous satellites are, but they're expecting that from that information, knowing that it stays above Ohio, you automatically know what the period of that is. Well, if it's staying above one place on the Earth, as the Earth rotates a full day, that's the period that the satellite has as well. So 24 hours, or however you want to rate it. 24 hours, one day. Or in all reality, we need to change it to seconds, because remember, everything when we're dealing with the period has to be put in terms of seconds. So I don't know if you know how many seconds are in one day, but if you don't, it's 86,400 seconds in one day. Obviously, you can figure that out just by doing some mathematics, but I'm going to go ahead and give that to you. Now, this question's asking, a geosynchronous satellite is one that stays above the same point on Earth, which is possible only if it's above a point on the equator. Such satellites are used for, well, don't know if that makes sense based on what I just said about Ohio, but anyway, such satellites are used for TV and radio transmission, for weather forecasting, and as communication relays. Determine the height above the Earth's surface such that the satellite must orbit. So we need to determine the height. So it's altitude above the Earth's surface. So again, if we go back to this problem, remember how far an object is from the center of the Earth is not just the radius of the Earth, but the radius of the Earth plus the altitude above sea level. So we'll have to keep that in mind. And then also, what's the speed that satellite is going? We're going to focus on C, and then it says compare the speed of the satellite orbiting 200 kilometers above the Earth's surface. We'll focus on that one in a bit. So when we're dealing with things like an orbiting satellite, so we have the Earth, of course, the center of the Earth, and we know this particular radius of the Earth, 6,380 kilometers. Oh my goodness, it's atrocious. My pen is going crazy. I don't even know how to erase. I thought I had a little erase button on here, but that is not the erase button. There it is. Okay. 6,380. Sorry, you're just going to have to watch me struggle. Okay, so then we have a satellite. I don't know. We'll make it a star that is a certain altitude above. That's really what they're asking. But when we solve some of these equations, we know that when we get radius out, it's going to be this entire distance. So we'll just need to subtract 6,380 from that. So if we were spinning a ball around in a circle on a string, we would know that the force of tension is what's causing the centripetal force. We learned that before. That's how we solved a lot of problems, how we solved the pig on a string problem, how we solved all kinds of problems so far. But we don't have this satellite with a string attached to the center of the Earth, so we can't use force of tension. What we can do is set the centripetal force equal to the force of gravity between those two objects. Because it's in a point, it's going a certain speed. Remember, we talked about yesterday. It's going at a certain speed that it's staying in that gravitational field. It's not escaping. It's not going too fast. It's not going too slow that it falls back down to Earth. So this is no different than spinning a ball around on a string where tension is really just the force of gravity. And then we can break this down to try and solve for, because ideally our job is to solve for the radius and then take that extra step to solve for the altitude above the Earth's surface. But I need to somehow break this down to solve for radius. So I'm just going to go ahead and start plugging things in I know. Centripetal force is mass times centripetal acceleration. Now let's think about for a second, what is this the mass of? If this is the centripetal force, what mass are we dealing with? Well, we're dealing with the mass of the satellite out here. So I'm going to put that subscript because, of course, I know force of gravity has more than just one mass in it. And then I'm going to write what I know as the force of gravity over here, big G, mass of the satellite, mass of the Earth. Those are my two masses that are attracting each other. all divided by radius. I could sub this radius of the between the satellite and the Earth, but I'm just going to leave it as r because I don't have more than one r squared. All right. So first thing I noticed before I move to the next step is that the mass of the satellite cancels out. It doesn't matter how big or small the satellite is, this equation is breaking down the same way. This doesn't help us solve for the radius because I need to break down centripetal acceleration even more. We know that's equal to v squared over r. So v squared over r is equal to big G mass of the Earth. It's important to keep that subscript mass of the Earth, though, because we don't want to put the mass of the satellite in. I don't even think they gave it to us. Over r squared. Now, what I see right here is that one of my r's can cancel out. So I'm going to cancel out one of my r's, and then I'm going to write v squared as what I know v is equal to. I know v is equal to 2 pi r over t. There's where our period is going to come in. So I'm going to go ahead and put in 2 pi r over t, whole thing squared, that's my v, is equal to g mass of the Earth, all divided by r. And then I'm going to break down this, I'm going to distribute the squared thing. Again, I'm going to get 4 pi squared, r squared, all divided by t squared, equals g mass of the Earth, all over r. Now, because I'm solving for the mass or the radius, I want to get my radius together. So I'm just going to cross multiply. I'm going to move up here on the next things. I'm just going in order here. So I'm cross multiplying. I get 4 pi squared r cubed is equal to g mass of the Earth t squared. So this is our first experience with, can you see it? We're going to get a cube root. So we have r cubed is equal to g mass of the Earth period squared, all divided by 4 pi squared. And then, of course, I want to take the cube root. So radius, the distance between the center of the Earth and that satellite up there, is equal to the cube root of big G, mass Earth, period squared, all divided by 4 pi squared. And that's a nice equation that we can just plug all the numbers in that we know. We know the mass of the Earth. Hopefully, at this point, you know the mass of the Earth is 5.98 times 10 to the 24th kilograms. If you don't know that, write it down somewhere. The mass of the Earth and the radius of the Earth are really important values to know. Go ahead and plug that in along with, we know the period I said on the other slide, 86,400 seconds. Because remember, everything needs to be in seconds, kilograms, meters, and then see what we get. So pause the video, solve for radius. Remember, that's not the answer to this question. That's just solving for how far apart the center of the Earth and that satellite are. They're actually asking us for how high above the Earth's surface they are. Trying to figure out how to erase this while you solve that problem. You should end up getting, if you do all the math right now, don't get discouraged if you don't get the math right. Just go back and try it again. You should get a radius of 4.23 times 10 to the 7th meters. And then with that, of course, we have to subtract. So 4.23 times 10 to the 7th meters minus 6,380 kilometers. Of course, those are not in the same units. So put them in the same units before you subtract them. And then a lot of times the elevation or the altitude of satellites is measured in kilometers just because it's such a big value. So you may actually want to change this value to kilometers. It's something that's often reported in kilometers just because of its magnitude. So change this guy to kilometers and then subtract them and then tell me how many kilometers, which you should get 35,900 kilometers. 35,900 kilometers above the Earth's surface. That's our answer to part A. That was a lot. Okay, so the second part says, what is the satellite speed? Now this is pretty easy because you have two options you can just plug it into this speed equation because you know the radius. Now think about what this radius is. This is not going to be the 35,900 kilometers. This is going to be the total radius that we got over here, the 4.23 times 10 to the 7th, because it's the distance that object is from the center of the Earth. And then we know the period, of course, is 86,400 seconds. So you can use that equation if you want. Here's another equation you can use, though. You can use this equation right here. It's not real clean because I just canceled some stuff out. But you can also use that equation to solve for velocity. So basically, you can say V is big G M E over R square root. That will also give you the same answer for velocity as this one. So take your pick or try both of them. It's a good way to check yourself. So pause the video, figure that out, see if you can find the velocity. And you should end up getting a velocity of 3,070 meters per second. Again, if you're not getting these right, try and try again. That's the only way you're going to not make the mistakes next time. And then the last part says, compare to the speed of a satellite orbiting 200 kilometers. So this is orbiting at 35,900 kilometers. But say we want to know what would its speed be if it was really low toward the Earth and only 200 kilometers away. So you can go back through, solve for the speed with that radius. Or again, you can do it over here because we know the mass of the Earth and we know the radius. You cannot put 200 kilometers in there for radius, though. You have to put 200 kilometers plus the radius of the Earth, 6,380 kilometers. Add those two together to put in your R value. Solve for the speed. Now, just like when we talked about Kepler's laws yesterday, and we talked about planets that when they're closer to the center body, they move faster. What we should expect is if the radius is smaller, and it is, than the example problem that we did, then the object should be moving faster. So you should end up plugging back into those equations and getting a speed of 7,785 meters per second. So see if you can get that answer, and that makes sense because objects that are closer then are going to move faster. All right, let's see. So I'm going to have you, now remember there's a few different equations. Any of the equations that we talked about, equation sheet or not on the equation sheet that we talked about through the notes, those need to be used. So I notice here on this next problem, they give me some period values, t values, and they are asking for a ratio of the radius of things. So you may be using Kepler's third law. Remember that equation that I told you was not on the equation sheet, but you do need to know it. So as you go through these last few example problems, I want you to put them on a clean sheet of paper. So example number 34 through 41, turn them in like we were doing before. I'll give you all these problems back that we've been turning in on the math packet. You can finish these problems, get them turned in, and then use whatever time you have left to work on your multiple choice practice test or the aviaries or the book work. That is all due tomorrow and Friday.